All right, this video is going to be on improper integrals. So first we're going to look at what an improper integral is, and then we'll look at how to work with them. So the definition of an improper integral is a definite integral. So if you remember, the difference between definite and indefinite is that indefinite integrals are the ones that don't have numbers and you integrate it and then you've got a plus c on the end. Definite integrals are the ones that have the numbers as an upper bound and a lower bound that you actually plug in and evaluate with. So an improper integral is a definite integral or any definite integrals that have infinity as a bound or they could have a discontinuity in the interval. So there was a problem that we had on an assignment and I had to skip it, and the problem was we were integrating, I believe it was from -2 to 3 of 1 over x to the 4th dx, and some of you guys had plugged it into your calculator and you got an error. And then we kind of talked about it and said, well, the reason you get an error message, the reason this is improper, is because 0 is in between -2 and 3, and 0 is a discontinuity. Right here, 0 is outside the domain of this function, 1 over x to the 4th. So we're going to say, why is it improper? It's because it's not defined at x equals 0, which is in the interval. So we want to look at how to handle these, and this is not necessarily an example problem, but it's more that instead of giving you some wordy definitions, I'm just going to kind of show you how this might work. So what we're going to do is we're going to consider a region. I'm going to call it R. We're going to consider a picture, because if you guys remember, integrals are actually the area underneath a curve. So we're going to consider an area underneath the curve. It's going to be under the curve y equals 1 over x squared. It's going to be above the x-axis, and it's going to be to the right of x equals 1. So a little sketch. 1 over x squared has a curve right here, and then also has a curve in the third quadrant, but we're only considering this part right here. We're looking at the part that's above the x-axis, underneath the curve, so right here, to the right of x equals 1. So there's x equals 1 right there. And we're going to shade this, and shade this, and shade this. And as you guys can see, that's actually going to go on forever, right? Because what we know about this graph is that it has a horizontal asymptote at 0. That curve is going to get close to 0, but never quite touch it. So if I want to know what the area underneath this curve is, I'm going to say that the area underneath the curve, and I would have to be able to cut it off to say that I know what to be able to evaluate this. So I'm going to say that the area underneath the curve is from 1 to t of 1 over x squared dx. So if I wanted to integrate that, I would think of this as I'm integrating x to the -2. So I can go ahead and add 1 and divide by -1. And so that is going to be -1 x to the -1 power, which would be -1 over x. And this is right here is being evaluated from 1 to t. So t, again, is that value that I cut it off as. So when we evaluate integrals, if you guys remember, we plug the highest number in first, so that's -1 over t, and then we subtract, plugging in the lower number, so -1 over 1. So that makes a plus, so I get -1 over t plus 1. That's what I would get when I evaluate that integral. Okay, so if we look at this, I'm going to reverse the order of these for a second. 1 over 1 minus t. So if you think about this area right here that's represented by 1 minus 1 over t, it doesn't matter what I plug in for t. There's no possible way that my area is going to be a number greater than 1. Because I could have 1 minus 1/2 if I plug in 2 for t, 1 minus 1/3, 1 minus 1/4, 1 minus 1/50, 1 minus something. It's always going to be a fraction. So I'm going to do 1 take away something. So my area has to be less than 1. All right. So you might say no matter the value for t, a is less than 1. So this means that as t approaches infinity, we can find the area. So what we're going to do is we're going to rewrite this integral. I'm going to say the limit as t goes to infinity is going to be 1 minus 1 over t. And if I think about what would happen if I plug infinity right there, 1 over infinity is essentially 0. So 1 minus 0 is 1. So that means that the area is basically 1. Now I'm going to go ahead and rewrite this so we can see how we're going to work with these improper integrals. I'm going to say that if I wanted the same picture but I wanted it to go forever instead of t, then the definite integral that I would be doing would be from 1 to infinity of 1 over x squared dx. And I'm going to say that because that's an infinity right there, I can't actually do this. But what I can do is use the idea of limits to help me come up with the answer. And the idea of limits tells me that if I look at the limit from 1 to t, if t is going to infinity, of 1 over x squared, that when I do all the math involved in that, I find that the area is going to be 1 of that whole curve going on forever. Right, so what that means is if we have an improper integral, we can take that improper integral and we can integrate it just like normal, and then instead of evaluating it between two numbers, we're going to evaluate the limit instead, and that's going to help us find our answer. All right, and then we're going to write a little note to ourselves down here. If the limit does not exist, like if this had been x squared instead of 1 over x squared, then we're going to say, then the integral, and remember an integral is actually an area under a curve, diverges. And if you think back to what we've talked about in other math classes, we haven't mentioned it in calculus, but you guys talk about it in pre-calculus with arithmetic and geometric series, either the sum of those either diverge or converge. It converges if you're adding up all those sums and it gets closer and closer to a specific number. It diverges in all the other instances. So I'm going to say that the area underneath the curve is going to diverge if that area underneath the curve is increasing without bound. So this area underneath the curve we were able to find because it was getting closer and closer and closer to that x-axis. Eventually we were going to have an area that's pretty enclosed, as opposed to a line that's just like going up forever. And that area would be getting larger and larger and larger, and we would say it diverges. All right, so what we want to be able to do is we want to evaluate improper integrals. And we have a few steps when we do this. So the first thing is we're going to go ahead and just integrate the integral, or integrate the integrand, which is the part right in here. So we can actually do the work with the function of integrating it. I know that the integral, or the antiderivative of 1 over x squared is negative 1 over x. That math is pretty easy to do. So we're going to go ahead and integrate. Our second step is to say, instead of evaluating, not going to evaluate the integral, you're going to evaluate the limit. All right. So now that it's going to be a little bit different if you're evaluating with infinity versus if you're evaluating a limit where there was a discontinuity, like there was a hole in the graph. So if there was an infinity, then you can think about what would happen if you kind of plug infinity in, kind of like we did with the 1 over t situation. If there was a discontinuity, you're going to use the left bound or right bound of that number. So if you guys remember back when we did limits, we would say 2 to the negative or 2 to the positive, and that would be come at it from the right side, come at it from the left side. So you're going to think about that. If the number is the upper boundary or the lower boundary, you're going to want to come at it from one side or the other. And I think that will make more sense when we do some examples. So use the left bound or right bound of that number. So when you think about what your answers could be in this case, we're going to say when you do those limits, if the limit exists in every single part, then the integral converges, and it converges to the value that you get. So if the limit exists, and what I mean by every part is that when you integrate something, it could be something plus something else minus something else. So it means that every single piece of that integral would have to have a limit that existed. So if the limit exists in every part, then the integral converges to that value. If any part of the limit does not exist, then the integral diverges. So we're going to have two parts to our answer. First, we're going to say converges or diverges. And then if it diverges, you don't have a number. But if it converges, then we're going to say what number it converges to. All right, now there's a note here. Special note. You can star it, underline it, highlight it, whatever. You can only have one discontinuity. Per integral. So if we look back at this one right here, you could not look at this integral and say from -2 to infinity, because infinity would be a problem, but also the fact that it has 0, it'd have two issues. All right, so you can't have two, you can only have one discontinuity per integral. If you have more than one, then you need to split the integral up. All right, so for our examples, the instructions are just going to say integrate. So for our first example, we're going to integrate from 1 to infinity, 1 over x dx. So step 1, I just have to integrate this. So the integral of 1 over x is going to be ln x. And I'm evaluating this from 1 to infinity. That means I can't actually do that because I can't plug infinity into a function like that. So I'm going to say the limit, and I'm going to give this infinity right here a variable to work with. So I'm going to call it c, as c goes to infinity. The limit as c goes to infinity of ln x evaluated from 1 to c. So I can't just plug infinity in here. But if I write it this way, then I can say, all right, I'm going to plug in c, ln of c minus ln of 1, and see what that equals. So if you're not sure what happens, if you can't picture a logarithmic graph or an ln, a natural log graph, you just need to be able to graph it and look at it. If you look at it as the c value or as the x value that you're plugging in gets bigger and bigger and bigger, it goes off to infinity. So we're going to say this is infinity right here. If you do ln of 1, you get 0. So infinity minus 0 is infinity. In the case of limits, we would say that that limit does not exist. You can't have infinity. We're going to say that this diverges. And so we cannot actually say what the area is underneath that curve. All right, for this one, we're going to look for the limit from 0 to infinity of e to the negative x dx. So first I'm going to go ahead and integrate this. I know that the integral of e to the negative x dx uses u substitution. So my u is negative x, my du is negative 1 dx, and I don't have a negative sitting in there, so I have to put that in the front. So I've got negative of e to the u du. So that gives me negative 1, the integral of e to the u is just e to the u, so that gives me negative 1 e to the negative x. Or negative e to the negative x would work just as well. So now I'm trying to integrate this, or evaluate it, sorry, from 0 to infinity, and I am not allowed to do that. So that means that I need to rewrite what I'm doing as a limit. So I'm going to say, I'm not going to do this. I'm going to say the limit as c goes to infinity. I'm going to go ahead and rewrite this. I know that that exponent of negative x means that I've got a fraction happening and that e is actually on the bottom. So I'm going to say I've got the limit of negative 1 over e to the x evaluated from 0 to c. So if I plug c in, that gives me negative 1 over e to the c minus negative 1 over e to the 0. So e to the c, any base raised to an exponent of infinity is going to ultimately go off to infinity. So negative 1 over infinity is 0. Minus minus makes a plus. Anything to the 0 power is 1. So this is 0 plus 1. So I know that the area underneath the curve is converging. So this converges, and it converges to 1. And we'll go ahead and do the rest of the examples in class.